This is actually a talk that we gave in Australia. So a lot of this work has been done by Soggy Kang, who's finishing up his PhD with me. He's in the same state as Lindsay. Both of them should have finished their PhDs a year ago, but I've absconded them for the desk, so I can't. But soon, yeah, all will return to normal. So these first slides are really a repeat of what I said yesterday, so I'm just going to kind of flip through until we get something that that I didn't talk about. But the bottom idea was that resistivity could be complex. We had that chargeability model, talked about things that were chargeable. We talked about overvoltage that was going on here, and we talked about an two-stage inversion, which is different, of course, than what you're doing. And that's one of the other things that would be really good to discuss here. And maybe that's a reason for bringing that landfill case history up, because there you do invert for all the coal parameters. But yeah.
The case I bring is,
pardon me?
The case I have on my stick is also for the
perfect.
TIP.
That's perfect. Anyway, so we've been using this two-step procedure. But the challenge with EM coupling comes about in two cases. One is for grounded sources. Might look something like this. And then the moment that you turn this off, then you've got this EM response that is generated. And the other is inductive sources, where we've got an inductive loop here. This is the region over those kimberlite pipes. There's actually two pipes. They behave quite differently. This is VChem data that's acquired over top. ZO27 at 90 microseconds. This is all positive. This is a decay, or this is, yeah, so you observe data for this pipe, and the dash line is for this guy here, so he's entirely negative. So there's two parts to this. One is how do we contend with the EM contamination and show a gradient example. That'll be a synthetic. And then for the inductive source, we'll actually revisit this kimberlite pipe. So for the time domain, well, for the TEM data, we can start in the frequency domain equations that look like this. So if we've just got a standard conductivity, here's the frequency domain, here's the time domain, and the relationship between J and E is just given by a multiplicative factor in both cases. In the Pelton model, we tend to work often with conductivity. So conductivity increases at higher frequency, and here's the real part, here's the imaginary part. If we take the Fourier transform of this, then we get a response function that has got a delta function, and then it's got this negative decay. So now I want to simulate the data. So the question is, how do we do that? So in frequency domain, you can solve each frequency with a complex conductivity, and then do an inverse to get what the response is in a time domain. Or we can directly time march it. So I have another student, Dave Marchand, who developed a time marching algorithm. And so now here, you need to contend with the fact that if I take the Fourier transform of this, then really my current density I've got is really the convolution of sigma of t, that thing that we just saw, with the electric field. So that complicates issues. You now have the convolution to take care of. So let's look at the observed response, if we've got an on-time system, we turn it off and we get something that looks like this. The part that we're interested in is this part here. This is the induced polarization part, but there's a time in here where everything is kind of contaminated by the inductive currents that are in your. So we're going to define a datum, and that datum is going to be whatever we measure. So there's here's our measurement, and we're going to subtract from that what we call the fundamental response. That term was actually developed by Richard Smith, I think, unless he got it from someplace. But this is basically how he defines. So you measure your data, and then you simulate your data at infinite frequency. So infinite frequency, there's no charges that have had a time to accumulate. So this is effectively no chargeability involved in this. So everything that is left over is considered to be an IP data. And if you take a little bit closer look at what is happening here, and you look at what is going on just after the shutoff, then we'll have an observed curve that looks like this. So that's this dash curve here, then with a positive IP response. The fundamental looks like this. So there's no sign reversal. And the difference between those two, the IP response, is this red curve. That's the guy we really want to find. And you can see that at early stages here, for early times, he is so small that he's not really, he's totally inconsequential. So this is, we call this the early time. This is sort of an EM induction time. We don't have to really worry about any IP. At late time, and this is where people generally want to be, just be recording at late time where the inductive response is gone, and now you just have an IP signal. But there is this intermediate area in here, which actually turns out to be important, where you've got bits and pieces of both of them, and you want to somehow separate it, because really what you'd like to do is to get this red curve back as far as possible. So at this stage here, there's no problem calculating the red because that's your observation. But as you go in here, you've got overlap and want to try to push that back as much as possible.
Sorry, what was the numbers on the axis? On the x-axis, 10, 100,000 milliseconds on the x.
Oh, on here?
Yeah.
Oh, yeah. So that's
Yes.
10 millimeters. Yeah, 10, 100,000. So here's a synthetic model just to show how that could potentially work. So there's 4 conductors in here. So there's A1, which is very conductive, A2, which has 0.01, A3, 0.1, and A4, which is resistive. So the background half space is 0.01. So that's the same as A2. A4 is resistive. A1 is a big conductor, and A3 is a smaller conductor. Okay, so we're going to try to see how those affect the data. And here's a cross section through each of them. So they're just blocks that are sitting. The forward modeling is, we're just going to use one source. So it's basically a gradient array source, which actually is often done in the industry. So put in current electrode here, and then measure the electric fields everywhere in between. So waveform is going to be kind of a step on like this, and measure data between 1 and 600 milliseconds. So the observed data, so here's the DC data. So this is what we'd have been talking about yesterday. You get this voltage. And if you convert that to parent conductivity, you actually get a lot of information. You see that this guy, yeah, can we shut that? So he comes out here as the most conductive object, and this is lower conductivity, and this is a resistor. So you're doing pretty well with the DC resistivity in that. What about data in the off time? If we now look at 5 milliseconds, so these are the decay curves, or the sounding curves for each of those objects. So this was the most conductive object. This is, yeah, this was essentially the background. I forgot to tell you something, I think. Sorry. Okay. Okay, so I talked about the conductivity. I did not talk about the chargeability. Okay, so let's make two blocks chargeable. So A2 and A3 are going to be chargeable. Okay, so this is really conductive, that's moderately conductive, that's resistive, that's background, and it's these two guys that are chargeable. So we want to find them. And each have the same chargeability and the same decay constant. Okay, sorry about that. So that's why we see A2, for instance, which was the same as the background. It's got this reversal in time, and you can see the the IP effect coming over here.
So that's a measurement just on top of A2, or how's that to be understood at A2?
Yeah, so this one's sitting right kind of in the center. This decay curve is kind of right in the center of A2, so it's someplace in there. At early time, at 5 milliseconds, that's this vertical line here. And you can see that for each of these different blocks, the IP signal is just well below. So we're in that really early time where we're just dominated by the EM induction. If we go to 80 milliseconds, so now we're here, okay. So for A2, we're actually we're starting to be affected by the IP signal, and similarly for A3. At 130 milliseconds, then now we've got still here's the response, here's the IP. So we've got a fairly significant contamination of EM responses in here. So at 130 milliseconds, there's actually quite a bit of mutual contamination. Actually, I've been concentrating on the decay curves. If we look at the plan maps, so at early times, basically what we're seeing is a distortion of that top conductor. At later times, we're seeing all three of these objects. This response is coming from the IP. There was no conductivity response. And by the time you get to this point here, both of these are kind of shining up as IP targets. There's still looking to be something up here. And at really late time, then you're in good shape. You've got IP target here and IP target here. Okay, so that's sort of what we're seeing in the procedure is basically as follows. So the idea is that at early time, you're basically dominated by the EM induction. So there's no hope of extracting any IP information in here. At intermediate time, that's an area where we can really make a difference. At late time, we don't need to do anything. but it's at that early time or intermediate time you really want to concentrate on. So now we're going to see what one could do from the point of view of EM decoupling, and we'll look at 80 milliseconds. So here's the observation. Here's the fundamental that is from the true sigma infinity. So now we do know what the true conductivity is in the synthetic. So if we go ahead and we do that, subtract that, then we end up with this as the IP data. So that's as good as we could possibly do. That is, that is the exact answer from a synthetic viewpoint. So now what we're going to do is to look at various conductivities that you could use to remove that EM coupling. So now we're kind of maybe coming back, a bit to more where you were coming from. So we take we have to have some estimate for what sigma infinity is, and the question is, okay, where do you get that from, and how well do you need to know it? And in this case, and sometimes in just ground work, you can get by with just almost using a half space for your background and not do too badly. So we use a half space here. So the IP datum is the observed minus the response of the half space, which is this, and it gives you something that looks like this. So this is quite wrong in the sense that we've got this big, large anomaly here, and that's definitely not an IP target that you're looking for. It does distinguish these two, although not in the right proper amplitude ratio. So how could we measure the background conductivity? We got a couple of options. Could use the late time DC. So we use this. That's still going to be contaminated with any IP effect, but we could go ahead and use that and get that as a conductivity, and then work with that. The other is that we've got these early time EM induction responses. So those are not contaminated with IP. So if we have enough of those times, we could actually use those to get a conductivity model and try that. So we'll do both. So the inversion methodology is standard. For the DCIP inversion, we're using SIMPEG, and for the other one, we're using a code here. For the if we just have a gradient array for the DC resistivity, you just have a single gradient, then you really don't have very much for depth information. So in order to get anything meaningful out of that, you need to use some kind of a depth weighting of 1 over Z cubed, because it's almost like a potential field at that point. You just have one gradient. So how does that work with the DC resistivity? We've got the true conductivity is like this, and we go ahead, we invert the DC resistivity. We actually do pretty well. We've got sort of conductors here. That's a resistor. It's a reasonable estimate of the conductivity. I now go ahead and use that to decouple. So here's my observed data. Here's the predicted that comes from that. And if I use, subtract those two, I get something that looks like this. So that's actually not bad. We've got these two guys going. So we've got rid of a lot of this, and we've changed the amplitudes here on this one. So that's not a bad decoupling at 130. So you still
Excuse me, can I ask you a question?
Sure.
When first you invert for the, you might say, the resistivity response using the responsive very late on time. Is that correct?
Yes, yeah.
How do you estimate that sigma S that you have up there? It's the one that is infinite frequency, right? Which is not the same as the zero frequency one, which is the one that you have actually used, isn't it?
Correct. Yeah. So there's there's a contradiction. There's assumption in here that No, there's a realization that they are different, but we're going to try to get by with it.
Okay, so bugger all, and we'll start with the DC resistivity.
Exactly.
Okay.
Which is actually what's done in most cases, anyway, at least for what we do, because we always do it 2 steps. So the first is, you know, get the resistivity from that late time data, and then you realize like, okay, no, that is contaminated by the IP, but we'll just do the sensitivities and go. So that's kind of where we are in here.
Yep.
So here's where, I mean, at some point, especially when the chargeability is larger, then you need to really start being serious about those effects, and that means, you know, doing a more complex inversion maybe. So take account of that. Okay, so that's with the DC, and so you can compare that with, that's what we have. That's the estimated IP data just using half space. That's with the DC. So you've really done a much better job by having a better estimate of the conductivity. So now the question is, okay, what about the TEM data? The idea here is that you're just going to choose those early times at which you believe the IP has not kicked in, and invert those early time channels to get a 3D conductivity structure. The result of that is this conductivity structure here, these 2 conductivity. Notice this guy is actually, can't see these very well on this, but on the computer screen you can. So this is a much larger conductivity than this, and this is resistive, and that's cross section. So if we use the that conductivity, here's the predicted responses. That's the fundamental response, subtract, and now we get this. So this is actually quite good, and especially in getting rid of this. So what we had with the DC conductivity, there was still, you know, some smithering of stuff up here. So that's actually done a pretty good job at 80.
That's also because you use the early time response, which would probably reflect the conductivity at infinite frequency. Is
right.
that correct?
Yeah, exactly. Yeah. Well, right, but this guy up here is not, he's not chargeable, this person here. So inverting the DC data over here, you know, potentially shouldn't be that much affected by that discrepancy between, you know, the DC data being contaminated with IP or not. So I think part of this difference is actually that, okay, we've got multiple time channels. In DC you have 1, right? But here you actually have multiple time channels. And an important part that I didn't mention here is that there's no depth weighting. So now you have a gradient array, but use multiple time channels, so you don't need a depth weighting. In the DC resistivity, with just that gradient array, it's like a potential field, so you needed the depth weighting. So I think that's, yeah, it's a potential advantage here in producing this. So here's the comparisons of the IP data. So here's the true IP data. Here's what you get using a half space. Here's what you get using the DC, and here's what we get with the TEM. So, this is arguably maybe even just a bit better. And ultimately, of course, what you'd like to do is to, you know, use both of these guys. So here's our workflow for the IP, same as before. We go and get the conductivity, which we've now done, use that conductivity for sensitivity, invert for chargeability. And this side's a little bit challenging to read in this light, but these are the different chargeabilities that we get from inverting, you know, from taking the IP data and having the EM coupling removed with a half space. So we get something like this. So we've got this great big false positive here. DC has got rid of most of that, and the EM has done a little bit better. So both of these are actually not bad. I mean, from the point of view of the IP inversion, yeah, they're not bad. I think we could argue that the TEM in this case has come out a little bit better. Oh, you can't see that at all. So anyway, that's okay. Anyway, if you do a volume rendering of this, then with the half space, you've got this other guy here, and with the DC and the TEM, you know, not so much different, but both have worked. But certainly the fact that I think what we were particularly proud of was that we actually did this, right? Took the early time data, inverted them, got a conductivity, and then used that. Right? So even though you could just use the DC in this case and get a long ways, the fact that you could use the early time domain data was kind of cool. And of course, now you can use both. I mean, you've got two pieces of information that you could do maybe even better. So I think the take home was that traditionally for these kinds of experiments, this early time TEM data is not captured, it's just discarded. People look at it, oh, it's contaminated, let's get rid of it. But by using that discarded TEM data, we can get a better estimate of the conductivity and the chargeability. So that was the take-home thing, I think, for the grounded source. The grounded source is challenging, but the inductive source is actually much more challenging. And that's now why I want to show this. So I mentioned this yesterday. So there's an area in Canada sitting up here. It's called Ti Kwi Cho, and that's very difficult to pronounce. Not as bad as Danish words or Swiss words, but so we just call it TKC, and it's in the Northwest Territories. This started many years ago in, I guess it was like the mid-1990s. Diamonds were discovered in Canada, and it was a big deal. And there was a diamond rush that went on, and everything was staked, and people were going out and just trying to find these kimberlite pipes and try to figure out where they, which ones might be diamondiferous. The techniques that were used to find them were basically magnetics and frequency domain EM. So it was, the discovery was made with a DigEm system, which is kind of like an older version of the resolve. And what you're looking for, so here is the characters. I talked a little bit about this. So these mantle eruptions come up, so they carry the diamonds in a stable state right up to the surface. And there's various types, excuse me, there's various types of kimberlite material. All these Ks are kimberlite. So this is a pyroclastic, that's volcanoclastic, that's hyperbyssal, doesn't really matter. As this stuff blows, so it blows up and then kind of falls back in. So there's sediments that kind of fill in on the top. And then there's usually a lake that's formed. So visually, you look for lakes. Look for a magnetic response because these guys are magnetized, and also a conductivity response. So they're basically going out looking for bullseyes of this. And here with the DigEm, you see two conductors. They collected both frequency domain data, and then this was about the time that the Aerotem system was, well, they were flying it on, I think, a pretty regular basis at this point, but they hadn't really flown it on kimberlite pipes. So they flew over here and in a couple of other areas, and what they were getting is that their at their early times, well, the earliest time that they could measure, they were just getting negatives. And at that point, they were just really perplexed. Like, okay, what is, what's causing this? It was known at that point, because of this paper by Peter Weidelt, that if you have a coincident loop system, that time domain signature from that for any three-dimensional conductivity had to be positive. And the only thing that could cause it to be negative is if there was some IP effect. So we've got negative values here, but at the time those data were taken, they just really hadn't seen IP effects or noticed them in airborne data. And typically what they do if they ended up having negatives, they just say, wow, it's just noise, we just throw it out. And that's actually kind of what they were doing here, except that it throws out everything. And so then they thought, oh, shoot, got to do something. Let's take the absolute value. So then they took the absolute value and then inverted that. That didn't work out all that well, but it's like, okay. Anyway, so they did that. I was actually at the conference where this was presented by Ken Witherly and Joel Jensen. And they were just really perplexed with this. That caused Airtem to come back and do a second survey. I guess maybe this actually is I can't remember if this is the first or second. But anyway, Airtem came out, yeah, this is the second, because the Airtem 2. And what they found is that they not only got the same negative responses up here, but they were actually even cleaner. So now they come back with a new system, you still get these negatives, and now they're cleaner. So you're thinking, okay, we think that's that signal. VTEM came over at that time, and they had signals like that. And then on ground, Nanotem had that. So no question that these signals were an IP effect. And then the question was like, okay, well, how we got two pipes. This one's negative and this one's positive. They're just, yeah, it's perplexing trying to figure out what was actually going on. In this pipe here, the decay, this is the DO27, it actually starts out positive and then it goes negative. So there's a reversal here. So that's indicative of chargeable material. So these pipes seem to be chargeable, and the question then is, okay, what do you do with that? So here was a movie that was made by Dave Marchant. So just to kind of illustrate what's happening if you have a loop source. So we're going to have a transmitter sitting 30 meters above the Earth. The background is 0.01 Siemens per meter, and there's a chargeable block in here. So there's it's just a background chargeable. It's not conductive at all. It's the same conductivity as the background, but it's got a chargeability of 0.1. So when the current is stepped up, so this is what we saw yesterday. So we get the currents and they're kind of moving through. So you can see, there's stuff, they're kind of circular currents going in and out of the board. So those currents are going in the same direction that the primary current in the transmitter is. And where we are in this stage so here's the sounding that you get if you're sitting right up here. So here's the curve. So it's coming along like this. It's all positive, and that's the time at which this snapshot has been taken. Okay, now we're going to run it a little bit more, and we're going to kind of get into this region here where it kind of goes down. So what's happened here is these induced currents have kind of gone through, but notice that these currents here in the block, and they're actually going in the opposite direction. So polarization currents always go in the opposing direction as to the primary current flow. So that's what's happened here. And now if you look at this point, we're sort of up here. So the block has, as those initial, as the inductive currents or inductive fields are sort of moving through that block, that's causing polarization currents to build up, and they just simply last a lot longer than these induced currents around here, and eventually that dominates. Okay, so that's sort of how that process works. So now what's the workflow to get this? We're going to invert the time domain data to recover, so the early time to recover an estimate of sigma infinity. Use that to generate the fundamental responses, remove the EM, linearize the equations, invert those for a pseudo-chargeability, and then we can use those, because we're going to do it at each time channel, we'll use those to estimate intrinsic IP parameters. So rather than, as what you would do, which would be to generate everything, put it all in one hopper and try to find, conductivity, chargeability, tau, and C, we're just going to do kind of independent time channels. And then
just a question: could you say that both in the DCIP and for the TEM, you basically use the 1D model as an extrapolation function?
No 1D. They're all 3D models.
Oh, sorry. But these models that you're obtaining from the early parts of the transient signals, of course, you cannot know what's going on further on with this signal, but you need to know what's going on with the signal in order to subtract it afterwards. So you're basically using a model which you have sensitivity in top for, and then sort of expanding it downwards as a sort of infinite half space solution. Yeah,
that's true. So in inverting the early time data, I mean, you're probably generally starting off with some kind of background model, and then your early time data will manipulate. It'll shape some of that.
Yeah. So it's really important what you put in sort of as your basement, or the lower part of your model, in order to, because that sort of sets the extrapolation that you're doing.
Well, as you saw, undoubtedly in some cases that's right, and yeah, your point is really well taken. Exactly. At what point those
I'm not saying that it's the worst. It's not necessary. I mean, here you know what you're doing.
Yeah.
Sort of in the steps, but it's just whether.
No, your point's actually really well taken. Something that we've thought about, but the even with the early time data, you sometimes you're still getting information.
Yeah,
perhaps from
certainly where you are in the level and so on. But if something happens further down that only gets a signature, for example, the temp signal, well into the IP signal, you will have error in your correction.
Exactly. Yeah. And yeah, the other place that it can cause a problem is here, where you don't have no positive data, right? So this is kind of interesting, and this particular example would motivate us to adopt more of an all-at-once approach for doing things, because here there's early time TEM data.
But that, on the other hand, sets a limit as to how much conductivity could be present. What I'm saying is that when the signal is entirely negative, it's probably because there's very little conductivity in that. It's very highly resistive, isn't it?
I think so.
Yeah.
So the fact that the signal does not become positive sets a limit to the maximum conductivity that would be present.
Right, or correct, or if you had gone back earlier in time, you could have made it earlier, then you would have eventually got there. But here, yeah, the conductivity is low enough, okay, And the
So what
chargeability
you-
is high enough that at the early times that you're measuring the first time channel, you're already in that negative zone.
But then sort of with the same overall approach, you could say, well, we will take a half space response for a conductivity which is definitely lower than the limiting conductivity. And we will use that and subtract that background and then
Yeah, I mean, that would be a first order way
Yes.
of doing it. Do something. Yeah. We actually had the ability, well, because we had the DigHem data, we could invert the DigHem data. Okay. And what we did was use a kind of a cooperative inversion method to invert both the DigHem data and the positive VTEM data. So to, I mean, this is actually, that was a challenging exercise, and it was really the result of a number of people, Mike McMillan and Sagi Kang, especially at UBC, because there's like a zillion transmitters here, right? Both in the frequency and in the time, and to be able to invert those data at the same time in a cooperative sense, that was kind of pushing our limits to what we could do. Yeah, and these are all 3D inversions, right? We're not doing 1D. So anyway, so what we did, took the DigHem data, which existed everywhere, took the the VTEM data that was positive, so that's anywhere here that's colored, so there's nothing very much up here. Inverted them cooperatively, got a 3D conductivity model now that looks like this. So this one up here is less conductive, so that's why we're not really seeing that. This guy here is more conductive. Okay.
Sorry.
Yeah.
The datum data, why is that positive for the up there? Yeah. Is it with another setup or?
No, in the frequency domain, because you've got always
Okay, that was
this.
the frequency domain.
This
The other
is
was the time domain.
Yeah, so this is the frequency domain system. So there is an IP effect in that, but because you're always basically looking at yeah.
So you're ignoring that.
Yeah, you're assuming it's not big. I mean, if you in frequency domain data, you can have an IP effect, but it doesn't show up as strongly in the data at these frequencies, so it was okay.
So the way it will show up would be in distorting the phase, I suppose.
Magnitude and phase, yeah.
Both magnitude and phase.
And I forgot what frequency. I think this might be the 7200 hertz.
So one's a lower frequency.
Yeah, they I mean, now they certainly go up higher, right? Anyway, so do that. Recover a 3D conductivity model in cross section. Looks like this. Actually, this cross section in here, and what was also captivated a lot of our time, because we had one of our sponsors, Tinto. They had been working on this site, and the person who was involved there was absolutely convinced that the high conductivity in this guy here, which is over a lake, was entirely due to the sediments at the bottom of the lake. And he did not feel that this thing should be conductive at depth. So we did a lot of analysis to try to test those two hypotheses, and our final conclusion is that the bulk of the conductivity at this pipe here has to be at depth and is connected with kimberlite. It's not connected with sediment. Okay, so now we do the EM-decoupling in a two-step method. So we take our observations minus the fundamental. So in that case here at 130 microseconds, these were the observations, and here's the fundamental. So we see it mainly in here. And if we invert those, or sorry, if we do that subtraction, we get this. Again, the quality of the image is not very good, but there's 4 places. So there's a region up here, A1, that is it's got a strong IP signal, A2, A3, and there's really not much here for it. So there's a couple of spots in here that show chargeability. At 410 microseconds, the results are more dramatic, and they're also more complicated on the observations. So you see down here, there's both positive and negative that are coming in. The fundamental response looks like this, and here's the IP response. So this, I think, is probably one of the most dramatic examples that we've seen with respect to the EM coupling. We basically got rid of all of this this red inductive response here, and now we're left here with just this IP signal. So there's A1, A2, A3, A4. Okay. So now we take, this is now done at each of 10 time channels, and we can invert each time channel individually. So this is the inversion at 130 microseconds. So again, this is a 3D inversion. Actually, calculating this is worth a commentary, because when Sagi and I did this work, we actually spent about 2 years trying to figure out what was going on. In retrospect, it shouldn't have been that hard, but sometimes it is, right? You just like, you're kind of walking around in a bit of a, then when you kind of understand it, it's like, come on, guys, like it's clear, right? But so what happens in an inductive source IP experiment when you're talking, 3D? Okay, so you turn that transmitter off, and for each location of a transmitter, okay, we got electric fields that are kind of diffusing through, and each of those, if you're at a particular cell in here, someplace in the earth, it would see an electric field that is moving through. It's got some kind of a wavelet that's attached to it, and it's also got some kind of a direction. Remember yesterday we were talking about this grounded source inducing fields into the into this object, and we just looked at the effect of the wire, right? And you could see that just the effect of the wire, first of all, had vortex currents in it. So we got currents that are going like this, and we also later on we had currents that were kind of going like this. So if you are inside a cell, then one moment you got an electric field coming in this way, then it's this way, different amplitudes and stuff like that, right? So it's actually pretty complicated. But each time that you've got a current coming in, you're charging up. So in that vortex system here, the polarization currents are actually vortex currents. In all the stuff that you're doing, with ground sources, it's just all kind of galvanic currents. So if you had a block, okay, a chargeable block, and you do your DC resistivity experiment over it, and then you look to see, okay, what way are the polarization currents? Well, then they're just parallel to, well, anti-parallel to the fundamental current. And so that's how you kind of think about what fields are. If you've got induced currents, those guys are going around like this. So then if you look at the polarization currents, yeah, and they're circular, they're going inside. So you imagine that things could become a little bit complicated because they're thinking a function of time. Now, what we're trying to do here is something that's intrinsic to a particular cell. So we've got one transmitter, okay, that's doing, just by itself, that's complicated. And now you have another transmitter over here. Well, he gives rise to a different electric field as a function of time. And so that's charging things up in a different way. And then it's like that. So the challenge with developing a sensitivity is that you really need to work with what the fields are going to be like for each transmitter at each particular time, and somehow combine them in such a way that in the end you've got kind of one sensitivity function, and that's related to a pseudo chargeability as a function of time. So the details of all that, which I think are very, very complicated, but we spent a lot of time because we wanted to actually make sure that we did this right, because there's a lot of stuff that's going on. There's some assumptions that are being made, and you want to test each assumption to try to find under what conditions things are going to break down. So that's all in that GJI paper. Anyway, I just wanted to bring that out because it's the airborne inductive problem is actually a lot more complicated than the ground problem.
So when you look at the IP inversion at various time channels, the time differences then kind of reflect from what kind of source the IP currents were set up in the first place. So that the earlier time channels would reflect the vortex currents, which die out normally a bit faster than the background currents, and the late time channels would then reflect the current systems at the late times, is where the vortex currents might have died out. Is that the way?
I think that's fair enough. Yeah, and because at each time there's effectively a sensitivity that's involved that takes account of what is happening, what the electric fields are as a function of time in a in a particular block. So anyway, at 100, so we've got the IP decoupled data, 130 microseconds, and those are now inverted. So this is now a linear, standard linear problem with the sensitivities that I sort of described. And this is what you see at the top pipe, DO18. There's a lot of chargeability that's sitting right up close to the surface. On this line here through DO27, there's chargeability much here. If I look at 410 microseconds, I see quite a different story. At the top, through DO18, it's just kind of decreased in amplitude, and through DO20, what used to be the dominant feature here is now decaying, and see this really large chargeability here. So definitely the chargeabilities are time, well, there's different rock units that are coming up with different time constants. So now kind of do one step farther. This is Superman's way of getting to the co-parameters, but here's our co-model, and we're going to, we've got data, we've got pseudo-chargeabilities at 10 different time channels, okay? And we can use those in a parametric inversion to find out the chargeability and the time constant. Okay. So now you've got this cube, okay? And over here in A1, just take a number of cells, okay? And each of those cells, you've got 10 pseudo-chargeabilities, and you're going to invert those to recover an intrinsic chargeability and a tau. Can't remember, we set C is equal to 1 or 0.5 here. I think it's 0.5. Anyway, so that now allows you to take the A1 and those cells, and you get up something that looks like that. If you go to A2, this guy down here didn't show up very much on the plots, but he's there. A2 is the yellow here. A3 is the red, so it's down here. So these guys here all have fairly small constants and a range of chargeabilities. If we come to the green object here, which is the main part of DO27, we see they all lie out here. So they've got much larger time constants than these guys. So there's definitely two different kinds of rocks. It's separating them quite nicely. I don't know, maybe there's some micromanaging that could be done to say something about these guys, but like sort of subclusters within a cluster, it's a bit dicier. So what's the impact on the kimberlite situation? These are kind of outdated slides. I have another slide, but better. But the bottom line is that we now have conductivity information from this analysis, and that allows us to kind of make different rock units with respect to this, and that can be compared with the drilling. And yeah, in another plot, I've actually, or another talk, I've got a much better image of that. But the rock model that we got from geophysics, I showed that yesterday actually. The rock model we got from geophysics and the rock model that was obtained from drilling was they were actually really closely aligned, and yeah, very informative. So here's a summary. So if we have grounded sources or inductive sources, then there's early time. Use that to get a conductivity. Here's your late time. Here's your IP, and we're going to work with the intermediate. So yeah, we first invert to get the background conductivity, and then we remove the EM responses. So now we're just looking at, here's the observations and here's the IP data. And now take the IP data, invert them, either with grounded system or inductive system, get that, and then may be able to distinguish between a couple of rock types. So, yeah. So that's kind of where we are with respect to that. That's all involving kind of two-stage. We're also starting to develop sort of an iterative process. Again, it's a question of whether you want to do everything all at once, where you now have multiple volumes to work with, or whether you want to kind of proceed in an iterative sense. And for us, the cards are out at this point. We're still going to continue with this because this stuff has been pretty robust, and so we kind of push that as far as we can. At the same time, one of the major reasons that we're excited to be here is that we really want to find out what you guys are doing, the problems that you're having, the successes, and just kind of where you are with respect to just looking at the whole problem. Certainly in that case where I was talking about at DO18, where the earliest times are negative, this is what we're doing. We should be just starting a nonlinear inversion with with all the parameters, do some estimate of what the background conductivity is, and just start letting things go. But, yeah, that's where we are.
So just a clarifying question. It's the fact that you have inverted every single of the time slices, you said 10 times, 10 delay times. You have calculated the sensitivities, and then you have inverted for the pseudo chargeability, as you call it.
Mm-hmm.
And then it's the very fact that you have that at 10 different times that allows you to sort of make a secondary inversion, which then says, well, that the different results that I get at the different times, they reflect that I have a chargeability and a time constant.
Yep. This is actually the same thing we did many years ago with another graduate student, Yuval Zudman, who published a paper under the name of Yuval, which has caused no end of complication. But yes, but there we were looking in a tailings area, yeah. And we had wanted to see if we could kind of get something about, I mean, there was chargeability there, but we wanted to try to kind of see if we could get some information about the state of oxidation and see if there was some differences. So we're trying to use, at that point, just the 2D DCIP, and we just did it at different time channels, and then inverted that to get co parameters. And it was informative. We also did it over a mine called Silver Bell, and we got some really interesting results, but we could not, we never had really good ground information to confirm that what looked kind of interesting from a numerical perspective was actually what was there. So it's, and then we kind of left that. We never went back to that, but now we're coming back more, I think, motivated by the airborne work, just to see if we can't get something, and maybe, and maybe even with ground work with permafrost, because there you have a very fast decay, and there might be something informative to be had there. So I think there's a lot of reason to go back. I think IP is just, it's just sort of coming to the point where there's just a lot of uses for it that people are just starting to get.
My impression is that it is, as you say, it's emerging more and more people would like to find the IP responses and treat them in certain ways, either qualitatively or quantitatively, as you right? But also that it's a lot of work, it's a lot of effort, it costs a lot.
To do the analysis.
To do the, yes.
Yep, unquestionably. Yeah, so that's that trade-off, right?
Yeah.
Well, it's also that same kind of issue that you contend with. Okay, so I've got all my airborne work. I'm just going to invert it, find a 3D conductivity, right? Do you actually want to put that into a 3D conductivity inversion, or do you want to do something like the locally laterally constrained, kind of do 1D and patch things together and work with that? And I think invariably, doing the latter is the best way to start out, and then you reach some point where, like, okay, things, maybe there's 3D effects that are coming in here. So
even, I mean, if you do, as everybody's, as you say, start out with, do a 1D inversion of your airborne EM data, you will still observe the IP effects. You will still be able to sort of locate the IP effects in space and so laterally, meaning, and in time, of course, meaning that you will still have a basis for doing exactly what you've been doing after your 3D inversions.
Yeah, and that's definitely true. We've had some airborne work that was done. We have another kind of a case history set called Mount Milligan. It's a porphyry deposit in central British Columbia. We've worked on that for years. It's just been kind of a test site. And there on the airborne data, on the time domain data, which is V10, there'd be, the data never go negative in these places, but they got little kinks and balances and things like this. And then you go ahead and you invert them and you find, like, wait a minute, these are really anomalously high resistivities, right? And so you're pretty,
off too.
Yeah, it's just falling off too.
They just don't go negative.
Yeah, they don't go negative, but they fall off too quickly. And yeah, so doing even a 1D inversion with those kinds of data can really highlight, like, okay, here's a region that might be problematic.
I have two questions for you, man. So in the example that you are showing is a data with the ground-based data. You are using C.1.
Or point, I'm not sure. Oh, at the let's see one. Yeah.
So my experience with 1D inversion of EM-IP data is that actually C is highly overlooked. I mean, what I mean is that the C value plays a significant role in the shape of these decays. And if you put a wrong C value, let's say, then you might get not necessarily a wrong tau value or you might get a wrong resistivity or a wrong thickness. And if you want to see, I have an example. So when you start to have only EM decays, you have plenty of equivalencies, and if you play, for instance, with 3-layer models, putting a wrong spectral content in the IP data means that you might fit, in any case, the data, but with wrong resistivity thicknesses. and is scary. So here, my warning is that, okay, many assumption of C is risky because you might go wrong.
And it would affect not the resulting IP,
No, it
but
goes
also,
to resistivity
also
thickness
the conductivity.
and the thickness. So then you start getting problems, right? And and again, in my experience, so the problem is that if you look at the lab data,
But you're talking about the TC case, right?
no, I'm talking about the airborne here.
Okay.
And I will example it. So the problem is that if you with lab guys and you present an IP model is C=1, you go to inversion and it starts to complain. Oh, okay, it's C=1, it's not physically possible and so on. And then if you look at the literature in permafrost and so on, you might find inversion of EM data that finds C close to 1. But in any case, my feeling is that if you look at the literature, all this frequency range where the IP kicks negative data is usually tau in the order of milliseconds or more. Depends on your system and on your waveform, right? But usually it's high frequencies. And when you look at lab data in high frequency, there is almost nothing, because when you measure in the lab, you have coupling in the system, and you always know, okay, and here I might have. You don't know what. So the problem is that we don't have a lot of knowledge of with respect to content at high frequencies. And what we usually map when we see airborne EM-IP is high frequencies. So the knowledge there is rare in the better case. But again, as many assumptions on the spectral shape as consequences not only on IP. Okay. And that's a warning. Then the second point is that, again, you might try to, and also if you start to put C values that are smaller, 0.5, 0.1, and if you talk with, for instance, Andreas Verb, is one good lab IP guy, he always says to you, okay, you know what, until 20 years ago, I was thinking that all the spectrum were flat. That means I was not big and they were flat at all frequencies. And in his experience half of the rock samples that he measured in the lab, they are reasonably flat in the spectrum. But flat in the spectrum means that there is a lot of spectrum also at high frequencies. And if you put C=1 or you put a flat spectrum, the EM-IP forward will be completely different. So this is just a warning. And then again, should we go for 3D and try to compensate for EM, or can we live with the 1D assumption but without doing all the approximation in the equation? Because if you go 1D, you can put your model for the spectrum and you can compute the forward and invert for the spectral parameter. And of course, the question is, okay, but if you have a 2D or 3D forward and then you invert to 1D SCI, what happens? Now we have examples because Shohong, I think you have seen this presentation at the NearSAPS conference on the 2D airborne IP. In any case, I mean, we have now 2D forward responses that we can invert SCI. Many are right, and we resistivity structure, but also the chargeability, and sometimes the spectrum. So again, should we go 3D and then make more approximation, or stay with 1D, live with the 2D and 3D effect, but these are easily recognized.
Actually do a joint, sort of all-in-one joint inversion.
All-in-one joint without any approximation, without any prior on Z, and with much more flexibility.
Yeah, but then you really increase that non-uniqueness that's coming in.
Oh, yeah.
Yes, but the problem is that you can always separate and then take resistivity from the other times. That's not always the case. So that's also a way of not seeing the equivalencies that are there.
But here's why I think this particular meeting is really interesting, right? Because you've got two groups kind of tackling things from different angles, and so it's an opportunity just to kind of compare and see relative weaknesses, and what's the easiest and most robust way to get through so that you actually get something out at the end that's not too fiddly and it's not taking too much time.
Under all circumstances, there's quite a few assumptions. I mean, whether you do 3D inversion and then you separate and you try to estimate the sigma infinity, and you do this, and then you have the different time channels, and then you invert that afterwards. I mean, it's it's a long series of assumptions and approximations. But the same is true if you do sort of a 1D inversion. You just can't have conductivity plus 3 IP parameters for each of the 30 layers in the multi-layer model. You just can't have that because, you know, equivalences just explode beyond the galaxy. So you have to have some assumptions anyway. So what I'm saying is this problem is really intricate, and therefore you have to sort of deliberately limit your point of view in such a way that you can get results out. You have to make fairly serious assumptions.
I mean, we're working a lot. I mean, it's almost 1 year now. We're trying to get a robust like scheme for 1 year. So these are tools, but of course the equivalencies are there. My point is that if you look at in the 1D world, you can study equivalencies. I mean, with this approach, you can study with Markov chain Monte Carlo, and then try to look at how big the equivalencies are. While if you do, I mean, in that approach, it's much more difficult where the approximation play a role or what kind of equivalencies you use.
True, it's easier to analyze the problem.
And my point is that the 2D or 3D artifacts also are easily recognizable because they always look like these effects. And if you have a strong residual contrast, you know they're there.
Well, when you're talking about inversion with 1D models, you're talking about few layer inversions, right?
No, multi-layer is more stable.
Okay. So multi-layer inversions, 4 parameters in each layer?
Yes. And inversion means it doesn't go crazy. So, and that's where we have been working a lot.
But my point still is that you have to have fairly strong priors to make this work.
No, I have examples.
Okay.
Not necessarily. So is it, you need tricks, yes,
Yeah.
but not with really strong.
Tricks! Well, did you see how he slipped that in? Like, it worked.
Just tricks.
No, I think it's fair. It's you have to pay attention how you dump your inversion. The damping becomes more critical, right? And then maybe inverting all parameters at once is not necessarily the best case. It's better to introduce some of the or the error bars in the data are important because all the places where you have change of sign are really critical, and if you don't increase the error bar there, then you might be easily trapped in a local minima.
Yeah.
And then you can start the model. So you need a starting model that at least for resistivity goes in the right order of magnitude. Yeah, it's a starting model, without any parameters. So I would say there are tricks, but they are not tricks where you are. It's if we're trying to stabilize a bit the inversion, because it's still a linearized inversion where you multiply by 4 the dimension of the model space with stronger dimensions. That's the case. But the point is that then, in any case, you feed the data well often, and then if you reach the point that you can feed the data, then you're sure that one, at least that one, is a possible model.
Just a side note on, from the instrument point of view, instead of sort of only focusing on trying to solve this very, very difficult equivalent inverse problem, what we could do in order to actually measure something that will help in resolving these equivalences. One of the things we heard about is if you could actually move a receiver at a significantly different elevation above ground from maybe your regular receiver, because then you could use the differences in field geometries between these two sort of different current types. You have one massive current at late times from the diffusing inductive current, and this very small scale IP current near surface. So they will have a very different sort of geometrical patterns in space. So if you could have one receiver at very high, maybe twice the height or something, then you will see a very different roll off with height from different currents. So that would be sort of a way to. So my question was actually, have you been working with that type of data? Because
Not us. Hadn't really.
We are.
Okay.
Hadn't particularly thought about that.
Okay, we've been hearing that they were this. So Because yeah, there definitely would be some sort of that would help significantly in reducing the ambiguity. No, okay.
So,
So what do you mean? Have multiple receiver coils?
If you could have an extra receiver in a different height, yeah, then you would be able to distinguish.
So would you put it higher or lower?
Either would work, I guess. There's a safety concern, though.
so actually, we did try. So we were looking first of all the sensitivity analysis, right? Because that's easy to complete. You do the analysis. It looks like okay. It looks like when you have two altitudes, it's better. But then we try with the MCMC, so going to Markov chain Monte Carlo just to explore the entire model space. And I'm more pessimistic now. So my feeling is that yes, the data are different, but when you go higher, the noise level is higher. And when you pair two receivers at different altitudes and two receivers in the same place, so same amount of data, they don't look significantly different from a statistical point of view. So honestly, they try receiver at higher altitude and a bird. And both of them, if you had asked me last month, I would be more optimistic. Nowadays, I would say maybe not.
But why is the signal level so much different? If you show late time signals,
Anyways,
it will be a lot.
nice smaller, right?
At early time, yes, not a late time.
In any case, I mean, we did try with I think reasonable models with NCMC and didn't look really so different. Still one, but the results of now are not so close.
Okay.
Well, maybe,
I'm kind of.
yes, I would say we should have a quick coffee. And then, do you have your presentations on the stick?
I have a presentation for another investigation. Yes.
That would be great.
Yes.
Because then we'll just put them all on one computer and
Okay.
easier.
I'm going to try.
So what problem are you working on, Lisa, now? What problem are you actually working on now?
What I'm doing exactly now is the temperature in Denmark.
The temperature in Denmark.
From
Yes.
all old data and newer data.
Oh, so to
Writing
look
I'm writing
historically.
a paper about how the temperature field is looking like in the upper 300 meters. What is the tropic? What is the thermal conductivity?
Oh,
We had a few years ago. We had a project on the possibilities of getting shallow. For that, I picked up all the old documents done from as early as 1980.
yeah.
So that's something about temperature gradient related to the borehole that they have been doing temperature measurement, take the entirety in the borehole. Which entirety is kind of gradient to look at. I have done the same with
So is this motivated by geothermal or is it motivated by climate change?
It was motivated by geothermal, but we actually got some climate change because my husband had two balls, and we had to do more investment. We invested in the balls about 1980, and now the new investments in 2012. And in Denmark, we have had temperature increase over the last 4 weeks. If you average like 15 years, what all the data from the meteorology, when they do an average I guess something like 15 years. You can see that
Sometimes.
Oh, no,
Half a degree.
no, it's more than, it's about 1 degree in 40 years.
In how many?
40 years. 40 years. Yeah. It's starting to increase. And you need some. And we take the boreholes, which is more or less the same time period from the 1980 and 2012. We have a temperature increase about half a degree. And then of course, like you have 250 or one is that down to 90 meters, the other one is really planes. Very nice.
Yeah, and also when there's time and
Oh, nice. Okay.
So that's what I'm
Det var det vel det samme som.
Yeah. No, that's
so we have to put a paper on.
Jamen det gør det. Den har jo ikke, den tjener jo ikke noget formål før at
Otherwise, I'm doing.
yeah, so
In this
No, I don't know.
But
Can you talk about that?
I'm going to talk about that.
Perfect.
We're here doing the geological analysis, and they are doing all advanced geophysics. So we take the results, try to do the geological modeling. So the case I have here on the stick is that we have a site where the and then pick it up. Figuring out so not really that proof that yellow proof that comes up into the street, and then they figure out something goes so not much but you need to kind of saying that the thin planet is very difficult to see some of
Yeah.
You have to think
Exactly.
Yeah.
That's
And then you can see the crane dive.
Yeah.
The crane is spectacular. Really stays strict on. Well, I think this is you really have to be careful what you do. One or the other, and one who you have really, and then you have to say, this is unrelated of what you can resolve.
Yeah.
So you know that one less probably a little land and
So, were you a participant? I think mentioned this guy. Were you participating in that project? Sorry. With the
Yeah.
Well, and that's first.
Every day.
The other one, the old one, I wasn't participating.
Because, let's see, where is let's see, IP. So, you got a second? Oh, I see. I'm still connected. Because that had the same problem, right? So here's the.
I guess you're more on the line field.
We were there.
Yeah. So. Yes. So. Yeah, so it's this guy here, right? So kind of right at the bottom, and then you've got this really low resistivity, right? But that could be, that could be the leachate at the top. And
there's also clay layer.
And the clay layer under below. Right? So then the IP is like, okay, maybe that's
yeah, then it's themes will be
Probably not
not 75 meters there, not.
Anyway, because no, I don't need 5 meters. Because that's that interpretation I just made, with this being more conductive up here, and now we've got leachate and clay, okay, both conductive. It's based on kind of like a single cell, but here's your model.
But I mean, eventually that one could be the chargeability from the clay.
Yeah, so that you think the chargeability is from the clay, but here's your cartoon.
Yes.
Right. So you got the clay lens and you got fluid up here.
Yeah, but the pollution often seems to come down.
Well, but this leachate is already not chargeable at all, right?
Exactly. It's only saline pollution.
Yeah. Yeah.
But I mean, funding also
right. But yes, like it's just like
So I would say that clay and also even clay.
So
you have the data. So I know that.
that's
Yes.
But to some extent, it's
most of this.
you have
Oh, but that was my.
you also get in the line.
And that one is that one has for sure a significant effect, I think. And we in some of the long profiles in recent weeks.
But I think some of
Most
they get more junction. You also see that.
Are there washrooms here someplace?
Restroom, there's one here on the right, straight, and then right all down there.
Jeg har lige taget en refleksion, godt ned kun af billeder.
Exactly. Ideas and contact.
Yeah, well, you know.
I've been doing some years now. Well, yeah, so I really find this kind of remembering, oh, yeah, but I'm doing a lot of okay.
So here was the.
There was this one kind of yeah.
And then the bottom one is the charges. So interpretation of what
yeah, but I was thinking that sediments where
Would you mind if we put it on a stick, or I can invite you to a hang because we're trying to capture video capture. If you're paying for that. Yeah.
Check if it works.
You do?
det dernede, det er
Actually, it's cheaper. It's cheaper to do
Oh yeah.
There's a lot
No, I guess 3D effects, I think, as well, depends on your
I don't know if you're talking
So as long as it's finally in the late times, if you're sure your data are off noise flow, very nice. Or if you have your case goes too fast. Then the problem probably yeah, I mean, you can be different, but then once you get 1 week, and I think
Kind of typical to the otherwise, it's so small that it's really small that you can start. Any kind of
Let's grab them.
Okay, guys, let's sit up. So is there anything else you want to present, or we're
I think so. I think you can just take over from here. Switch.
where can you present it here?
So how many people do we have that are presenting? So you've got,
Yes.
you've got a couple, right? And
Yeah, I mean,
You have one, two on this. There's two on here.
So what I'm going to show you is briefly some of the things we've been doing the last year, mainly together with Sean. He's a professor from Beijing University, is downstairs. And so what we've been doing is to generate 2D forward responses for an urban system, a SkyTem-like system, in 2D, and then try to invert them with the 1D LCI, try to find a kind of robust scheme, where robust means at least not too much painful. And I'm going to show you examples. So first of all, so this is the kind of data that we look for, invert for. So it's positive and then becomes negative. And whenever you see a change of slope like that, this means that the signal became negative. And this is a kind of a crucial of the 2D forward solution. And the difficult part is always to get the data where you change sign accurately. We were playing with 3 kind of models. So all of these are 2D models. We have a chargeable anomaly embedded in an Earth rock that is not chargeable, and we have 2 kinds of cases, conductive and resistive models. So in the conductive models, we have 100 meter in the Earth rock and 10 meter in the chargeable body, and then the Earth rock is not chargeable and the chargeable body is chargeable with a few hundreds of millivolt by volt for M0. So for the resistive case, we have 5,000 meter for the host and 500 meter for the anomaly. And then again, we have an infinite block, a long block, and a small block. And here we have soundings every 20 meters. And this is 1 kilometer fly. So if we give a look, first of all, at the data to see how the 2D data look and how the 1D, the equivalent 1D data look, because they look different, sadly. This is for the resistive case. So this is our noise floor. In red, we have the 2D forward. And this is station A, so we are just outside the chargeable body. So there is still a change of sign in the forward data, but it's below the noise floor. So this is something that would be difficult to detect. If we go to a station that is on top of the chargeable body, you still see 2D effect. And this is why the time of the change of sign between 1D and 2D is different. So they are still different. But they start to be more similar when you go farther on. They are, of course, identical, and the same when you go in the Earth rock. So this is the resistive case where the signal is low, and then for the conductive, so 100 meter for the Earth rock and 10 meter for the anomaly, the signal is much higher. Again, we have a difference in the time of the change of sign between 1D and 2D. And when you go just outside the chargeable anomaly again, there is no change of sign at all, but you still clearly see 2D effects. How much this 2D effect is 2D conductivity or 2D IP, we are working on it. Probably both of them, but mainly conductivity. Briefly, also the other 2 examples. So again, just outside the anomaly, again change of sign for the resistive medium, but still in the noise floor. But you have this abrupt change of sign, probably still IP effect. And then you have in the center of the anomaly still significant difference between 1D and 2D. And the same for the conductive. So no change of sign, just outside the anomaly, and difference in the data. So this is somehow scaring. So this means, okay, but can you deal with 1D when the data looks so different? This is what we're trying to look at. Finally, for the small anomaly, so this is really narrow. There are no negative in the 2D, and the 1D, it will be plenty of negative. So the 1D solution here, clearly with the same chargeability, will be quite off. And for conductive is the same, because there are no negative in the 2D signal in blue here, but still there's a clear shape that you cannot fit resistivity on, because you have this strong change of slope. So the data are 2D, and now we're going to see how the 1D assumption in 1D LCI inversion scheme will deal with this difference in the Earth space. And the idea was to try to have, in any case, an inversion is more robust than a classic call inversion, putting 4 parameters in inversion as it is. So we tried to do 5 types of tricks for improving things. So first thing was to use a different parameterization. And I don't have a slide for that, but the idea is that when you have a conform model, and you look at the complex maybe, you look at the complex conductivity, the complex conductivity increase, and then you have your phase stick. So this is sigma 0, this is sigma infinite, and you have sigma infinite minus sigma 0 equal m0 divided by sigma 0. So the distance depends on m0. The idea is to use, instead of m0 as inversion parameter, to use the maximum phase shift. And the reason for, so again, you have still 4 parameters. They are completely equivalent. You can go from one parameterization to the other. But our claim is that if you invert for rho p max tau phi, that is the inverse of this peak of the parameteristic, and C, this is a better parameterization than rho m0 tau rho and C. And the reason is that these 2 parameters are less correlated than these 2. And when you do multi-parameter inversion, if the correlation is smaller, you're right. When you look at ground-based data, so if you do galvanic TCP, this is particularly true. So you get a significant improvement in the resolution of this parameter compared to that. When you look to airborne, honestly, equivalencies are much bigger, and then the improvement is significantly smaller, but still there is improvement. So this means instead of having M0 reta in your notation for the chargeability, we have the maximum phase shift. But this also means it's much easier to compare this inversion result with lab data. Because if you have lab data, you have your spectrum, you usually have the spectrum either in phase or in imaginary conductivity. But phase is also a typical thing that you have. And then if you claim, okay, I see 100 milliradians or 50 milliradians, that's much easier to compare to lab results compared to I have 200 millivolts by volt of M0. No one knows how to compare to lab data. So the first thing was to use a different model. The second thing that we do for the inversion is that we try to get a good starting model. Well, good starting model here means mainly good resistivity. And we do something where we take the positive data and we invert for homogeneous space all the data at once, just for getting the order of magnitude. Because of course, if you start completely off, then you might either you don't converge or you are trapped in local minima. And what I'm showing here in this plot is the misfit of 6 inversion. So I presented to you 3 models. So infinite block, long block, small block, conductive and resistive. So we have 6 models in total. And in red, we have the misfit if we use the classical call. No, sorry, this is if you use an average resistivity, in this case, it's an 100 meter. So resistivity is off compared to the average resistivity, and in black is what you get if you use a reasonable estimate for resistivity. So again, we are doing linearized inversion. You need a decent estimate for the starting resistivity. And I think this is fair. So this is something is not surprising anyone, I think. Then we need a good STD model. Where here means that we put big error bars in the data where you have the change of sign. In that datum and in some of the data close to that one. And the reason is that it's difficult to get that value, especially in an iterative inversion. If you have a normal error bar there, it's really easy to be trapped. And then you have a final miss is much higher than what you can get simply increasing the error bars in 2-3 gates. Then we don't let free count C since the beginning. Take it easy. It's difficult, so we let them free after, in this case, 7 iterations. And this, again, improves significantly the final misfit. And then we use a different damping scheme, where we dump differently the different type of parameters. So we use a damping for resistivity, a different damping for phi max, tau, and C. So these are the tricks that we use.
In which way are they different? I mean, is
The
the magnitude, I mean, is the strength?
So
of
our
the
typical damping scheme was to use one damping value that is linked to the maximum diagonal, so the maximum diagonal element of all the data, right? I mean, you take the maximum elements and then you dump compared to the maximum element of all the model parameters. Sorry. In this case, we take the maximum for each of the parameters differently. So we don't overdump tau, c, and Tmax. So the idea is to try to not overdump parameters. Otherwise, they don't move when you are dumping a lot, and then you might be trapped.
So if you had kept to m naught as a parameter, chargeability, then when that becomes small, then you have no sensitivity whatsoever to tau and c.
Yes,
That's
that's clear. If there is no chargeability, there is no tau and c.
Right. Okay. So how does going to the maximum phase angle?
So the maximum phase angle
how does
actually,
that kind of
so
work?
the idea for the maximum phase angle, and sorry I have to go again for the streaming, is that when you look at this spectrum, the classical cone, if you change C in this spectrum, what happens is that your phase decreases and becomes wider.
Yeah.
But if you change M0, your phase decreases. And the problem is that when your spectral content is limited, a decrease in phase due to the change of shape or due to the decrease of the maximum value might be almost the same. While if we use Tmax and C, when you change C, the maximum phase remains the same. In terms of call means that you have a bigger M0. And this means that C and phase are less correlated than M0 and phase, M0 and C. And simply for galvanic ground-based data, that's really you. If you look at the standard deviation of a MCMC inversion, you get easily 1/3, 1/5 of the standard deviation of Tmax compared to M0. So it's really significant. With airborne, we get 20–30%. Honestly.
But in the end, eventually, the parameters that you wish to get out to be indicative of what it is that you're investigating is M0, right?
Is sorry?
I mean, it is the M0 parameter that you want to get out.
No, I think honestly, this is something you can discuss with lab guys, right? Because M0 is something that the field guy likes because you can invert your data with the call model. But if you talk with lab guys, they don't care about the call model, the call M0 values of this spectrum, right?
But the people who have a practical problem of identifying various parts of what is dumped in the dump site, which parameter would they like to look at?
Anything that shows an anomaly that is significant for them. And my point is that Tmax is going to be more significant.
So they're only interested in sort of qualitative results anyway?
In dumps, I would say so. If you want to do anything quantitative, my point is that Tmax is significantly better than M0, or eventually, another thing we will do now is to look, instead of amplitude and phase, we look at imaginary conductivity, so sigma first and sigma second, and then we look at the yes. I think I didn't say it. So you look at the maximum imaginary conductivity, and these two things are the things that you can easily compare with lab results. And this is really close linked to what you usually play with in interpreting operation. So my point is that not only they are better to invert for, but they are also more interesting for any
eventually more indicative of what
yes
what is going on mythologically.
Yes.
My point was you do not. I mean, well, my consideration was that if you invert for the maximum of the phase, then eventually afterwards you have to sort of invert that to give your M0, and then you have, I mean, difficulties can be moved around, but you'll end up with your difficulty there instead of in the inversion, right?
So my point is that as long as you do a deterministic inversion, right, you get to the final model. I mean, for any inversion cell,
Yeah.
I can convert this
No,
model to M0.
I mean, I take your word for it that that the maximum phase is at least as indicative of what is going on as the M0 boost.
What I'm also saying is that you can always, in any case, go back. But the problem is that if you look inside the deterministic inversion to a complete MCMC inversion, then Phi-max will be better resolved. So having the results of the linearity inversion for Phi-max will probably be close to the peak of the distribution of the parameter in a complete inversion. Having the solution of an M0 parameter in linearity inversion can be a point of a very broad distribution where this is less indicative of anything helpful, in my opinion. And this is something that honestly you learn by doing, because when you play a lot with inverting also for C, letting C goes to the values that the guy in the literature claims are realistic values, or small values. When you invert M0 and C, you have two fantastic mirrored images where you're looking at correlations. And then you're not really right, because if two of your sections, they look the same, except that they are somehow mirrored, this means that you're looking for correlation. And when you invert for Phi-max, this is much less there. And then you're okay. But if you want, I have more details on this.
So you're saying that within the context of your inversion with C and M naught, that you can basically change C
and Phi-max or sigma second max, and that would be a better job.
No, but that there's real strong correlation between C and M naught.
Yes, so those are really strong.
And do you know, to first order, what that approximation would be? Is there something that's kind of equivalent there, like some product of these things, or
that's more difficult. But in any case, you increase M0 and you lower C. And if it's a product, I don't think so, because also the range are quite different. But they're strongly correlated and not necessarily linear. So if your bars are big enough or C is small enough, then if you look at the correlation, they are not linear correlation. There's even more. Okay, so these are the tricks that we play with, and in my opinion, they are they are reasonable tricks for linear inversion. And then we look at inversion results. So this is the infinite block anomaly. Here I only the complete Kolfol inversion. So the anomaly is here, and it's 10 meters, so it's in the right range. This is Phi-max, and it's I think 150 millirad, something like that. So it's again in the right place. The black there is the depth investigation somehow. This is tau, and again we start from the green value and it goes to the yellow, and the yellow is the right one. And C, we start with 0.3 and we get to 0.5. That's the true value. These data are without noise. So we have the right error bars compared to the noise level, but we didn't add random noise just to see a this misfit for giving an interpretation of this misfit. So this is a 2D misfit somehow. So this here we have 3% error bars on the data plus I think 1 nanovolt per square meter of noise, and we can get to a misfit around 1 with the 1D solution. Does that mean that the 2D and 1D solution, they are far apart only 3%? No. This means that you compensate the 2D effect somehow with the value of the parameters, slightly with the thickness of the anomalies. But on the other end, the final model looks really what you look at. And you resolve also the spectral parameters. It's almost unbelievable from my experience.
So in this case, just a sec, so you didn't add noise to the data, is that correct?
Yes, the data looks, I have them somewhere here.
Okay, so you've used exact synthetic data.
Yes.
And now you do assign some kind of percentage and a floor, even to the synthetic data.
Yes.
And now you're coming along and you're going to invert those, but in places where you get large misfits, you're going to allow a bigger value of effectively change the uncertainties to be to be larger?
No, so here the uncertainty are assigned at the beginning, right? So the uncertainty is 3% plus noise floor plus bigger bars on the change sign, and you assign them. Then you have two options. Either you add Gaussian noise, right? And then it's better if you do it multiple times to be sure it's stable. And we can do that, and you get good results as well. The reason for which we didn't do it here is that we wanted to see what kind of misfit we get, because this is also a dimensionality misfit. So here the problem is that this is 2D forward, and not necessarily we can get a misfit equal to 0 without loss.
Right, but in your inversion, you're actually allowing. We've got
So these are the
misfits.
The misfit goes to 1, so within the error bars here, and not below 1 because there are 2D effects. We can fit them down to 0.
Fair enough. Good.
So this is the small block, and again works I think quite well. And again you get all of them, a bit shallower, but again you get all of them, and the misfit is still around 1 in the center, where the difference between 1D and 2D is bigger. And when you go to the last example, so this is only panel-like effect on the resistivity, but in Chargeability you still see it. So honestly, we are quite happy, and there is also something in C as well. This is just to say again that C is an important parameter, more than tau, sadly. These are the conductive example, and no, I think I don't have the resistive here, but they will be less good than that because the noise is bigger and means that we have many negative data with really big error bars. The last slide is on the warning about the equivalencies. So this is an MCMC exercise. So this is a Markov-Chain Monte Carlo inversion of a 3-layer model. So we have one 3-layer model is a kind of equivalent of this infinite block, but with a continuous layer. And we have MCMC inversion with a classic call with the NPA. That is the model I was showing you, and with a constant phase angle, where the constant phase angle is a model that has only 2 parameters, where there is the sigma infinite and there is the phase. And is the limit of C going to 0 because it's a flat spectrum. So it's the simplest IP model that you can play with. And it's an IP model that in any case describes half of the data you find in the lab. So here the point is that, so here what we're looking at is 5 different inversions with different C values, from 0.2 to 0.6. So we change the shape of the spectrum, and we keep resistivity and phase at the same level. So the phase would be 100 milliradians for the chargeable body, and we're looking only at the second layer. So this is the chargeable layer between the first and the second layer. And we have here in these points we have the median value of the MCMC inversion with the error bar, with the standard deviation computed from the MCMC inversion. So we're looking how well we retrieve the true value with the MC inversion. And my point here is to look mainly at the differences between these two. So maximum phase angle and constant phase angle inversion. Maximum phase angle has the freedom of changing the shape of the phase, while constant phase angle keep the phase the same. So my point is that if you look at the true resistivity value, the constant phase angle goes to twice the value. Instead of 10 millimeter, finds 20. And if you look at the thicknesses, especially for big C values, it means where the spectrum is not flat, the thickness of the first layer is underestimated. So you take the wrong spectral content, and you get a fantastic equivalent model where the equivalence is in resistivity and thickness. And this makes things more difficult, because if you put the wrong spectral content in your inversion, you might probably be able to fit the data almost equally well, and you get different thickness and different resistivity. And then good luck. Again, mainly I guess it's more scaling part is the thickness, right? Because then you go to the driller and say, okay, drill there, you find it at 20 meters, maybe 25, maybe 30. And it's because it's the spectral content is wrong. And I was surprised when we found this. And misfit-wise, just to say the complete story, for small C value, you fit the data perfectly well. For high C value, in this case, 0.6, the missing, instead of being around 1, is around 1.3, 1.4. Again, when we talk about 3% error bars, that's a small miss. So this is something that when you have change of sign in the data, you still fit the shape, you will be happy with. And then do you go for the simplest model that explains your data, or for a more complex one with bigger equivalencies that might get you a bit better estimate of the median value? I don't have any answer about that. So I try to explain better the figure again. So this is resistivity, and we have 5 values for each of these C values, and these are resistivity of the second layer. So resistivity of the second layer, you find it quite well. Honestly, the error bars with small C value in the MPA in this case is worse. So this is where it's not behaving better than the classical code. If you go to the phase, so in this case, the phase is always 100 milliradians here, and this means that the equivalent is 0 change. Because if you change C and you want the same shape, you need to increase in 0, right? In this case, the phase compared to the RCC is better resolved. We are around 30–40% smaller than that. Not exceptional, but better than that. And okay, for tau, no, here there is an error. In the figure, you have the right one. Here, the error bars are bigger, are similar to this. So the true value is better represented, but the error bars are comparable. And C, again, you find it. So for C, we have sensitivity to it. And the thicknesses, you find them correctly if you use 4 parameters, and you will find the wrong one if you use only 2. And again, if you use only 3, so if you fix C to any value that is different from the true one, and you compare for tau as well, you will find again wrong thickness and wrong resistivity. And this is on the scary part of the conclusion. Any question?
No, but it's an interesting result. Worth a further in-depth look, certainly.
And again, my point is that in any case, the linear inversion works, I think, reasonably well. And if you do here a constant phase angle inversion again, you fit the data almost equally well, and the thickness of this chargeable layer will be slightly different. And then the inversion compensates. But I mean, sometimes thickness is what also you look at. So here's a warning to say there are plenty of equivalencies there. Not only between RT parameters, but also between RT parameters and classic ones.
Let's see. So you said when you use a constant phase angle.
That means only the first 2 parameters here, practically.
Right, and then the true value of C was what?
In this case, C in the anomaly is 0.5.
0.5. So effectively, assuming that C is 0 and going ahead and doing the inversion, still gives you reasonable results. Is that what you're saying?
So reasonable in the sense that you get the anomaly, right? So the anomaly, you find it where it is. The value of the resistivity or the thickness of the anomaly, you have a bias. But you know,
but you haven't thrown the baby out the bathwater.
But depends, right? Because I mean, if you have 2 parameters instead of 4, everything is much simpler, right? So you gain a lot in simplicity. So I don't think there is an easy answer to that, where to go for. My point is that 2 is often enough. So not even 3, also 2 is enough. Okay, too much silence. That does not sound good.
Yeah, no, I think it's just that, you know, this is the kind of thing now you got to go back and
Yeah, I mean, this is
carefully,
why whenever I see an IP inversion with call, I'm really interested in C, because from my experience, C is one of the most troublesome parameter there, because it plays a role and you are not interested in usually about that. You often look at tau, thinking, okay, tau is something that can be linked to any diffusion length and whatever. Yes, but C is by far better resolved than tau. And then this regarding C might be risky.
In that vein, the results that we showed with the TKC model, so when they were inverted to get chargeability and tau, so in the constants, okay, they were actually done just assuming C was equal to 1, and in the other one, C was equal to 0.5.
But then tau is completely different, to my experience. So again, the bottom message is that C is important. And C0.1 or 0.501 is different words. I mean, they look really different shape.
I would really like to see a certain type of plots here. And so it's just two-dimensional plots where you have one parameter up, one axis and another one out. And you take all of the possible combinations. And then you take, you just do forward modeling around the true model. And then you plot the residual. And that will enable you to see what the equivalences actually are. Yeah, the shape of the equivalences, because you can get them this way, that
Depends
way,
on how the problem
this way or that way, and you can also play around with plotting it linearly, algorithmically.
This is where honestly,
whatever. I mean, so it would enable you to get an idea about actually exactly how
my answer is no.
These parameters will couple.
My answer is no, and this is my reasoning. Maybe I'm wrong, but so we started looking at. We start to look first of all, for instance, at the simple analysis, right? And you start with the modular subspace. And in modular subspace, you're happy. And you're happy because you prove clearly, for instance, that the MPA is significantly better than the RCC. And then you start to play with 3 layers. And then you start to see correlation between parameters you will never think that they should be correlated. And the correlation becomes strong and between many of the parameters and not linear. And then you need to try to explore more the model space. But the problem is that, I mean, these are preliminary results, and we have only 1 million of runs in the MCMC. We need probably 10 million of them. And handling the boundaries where M0 goes to 1,000 is not simple. When C becomes small, it's not simple. So it's not an easy task.
No, what I'm suggesting is that you just explore it around the true model.
But around the true model shouldn't be then. So around the true model is similar to look at the sensitivity, right? And the linearized.
Yes, but I would just like to see them cross-plotted between all the possible parameter combinations, because it would enable you to actually identify what kind of equivalence is subject.
Yes.
It's a sort of a visual aid in actually identifying and understanding the equivalences.
But again, my experience so far is that when you look for multi-layer models, 3 layers, that often is interesting, right? Because you look for a chargeable anomaly in a post-rock. You have correlation between many of the parameters, and then you need really many of these plots, right? And
yes, you need, I mean, how many times can you pick 2 out of how many parameters that you have?
Exactly, but the problem is that many of them are important. and then the interpretation
just
becomes
do all of them
right?
and then throw the ones away that are not important.
Exactly, but there will be only half of them. The other half will be important.
But you will only find out by doing it.
No, but I mean, the MCMC is thinner, right? I mean, we look at the distribution of all the parameters and we look at the correlation of all the parameters.
Yeah. But if you've done the MCMC, you'll probably be able to extract those plots.
Exactly, and my point is that there are strong correlation.
Do you have, I mean, you're really trying to find a 4-dimensional function here, or 4 functions, right? So, there's potentially, regularization in depth, okay? And there's also regularization for each of the parameters as function depth. I mean, if you open this up to have a large number of layers, is there anything extra that you need to incorporate from the point of view of regularization to help you step through these things?
So the problem is that forcing a privacy value, to my experience, is risky because you can easily go in a local minimum. Tau, that's relatively easy to start with. I mean, you want a tau value that triggers negative data. And I think you have 2-3 orders of magnitude where to play with. If you go to really small value or really big value, you won't get any negative data. So getting a starting value for tau or a decent guess is not too difficult looking at your data. Depends on your system response. And I mean, once you have defined the system, you can play with the homogeneous space and see what are the tau values that trigger negative data. C, we start at 0.3, so a middle value in our experience because we don't know where to go. For resistivity, it's important to have a decent starting value. For phi max here, we always start with moderate value. Where moderate in this case is 30 milliradians. It means 30 does not give any significant IP effect. But if you move it to 50, 60, then you have it. So it's just below a significance. So for the inversion, it's not too difficult to bring it up. And with this one and the same kind of constraints on all the parameters, we get reasonably good results. And then we work for all of them at once, and we don't get too many prior on how these things look. So our work was mainly try to get this inversion somehow robust. That means you run them and you get always a decent inversion.
Without too much pain.
Exactly. I mean, some pain, but not too much.
Do you want to put the next one?
Up to you. I have one presentation on different parameterization to show a bit more in details how these look, and another one about hydraulic permeability. So 5 different.
Perfect. Which one would you like next?
So let's start with the parameterization first.
This one? Or?
New models, yes. Okay, so this is something we've been doing again since the last year at least, and the idea was to try to break down the correlation between M0 and C, because those ones were too sad when you were looking at your inversion. So a classical way of describing the total conductivity of the medium is to think it in terms of a parallel of the bulk conduction, the surface conduction, but the C part, or the real part, and then the imaginary part of the conduction is our polarization. So this is often how you write your equation in kind of extended Archie's law. And the problem is that these are also frequency dependent. And the classic way of writing these frequency dependencies is to use the Kolkol model. This is the most used model when you invert real data, and the most hated model from lab guys, I think. And this is an expression with sigma 0, and would be completely equivalent with the expression with sigma infinite that you were showing, right? It's simply playing with M0 and sigma 0, and then you get the same. So the inversion parameter are again sigma 0 or sigma infinite, M0 or eta, and then tau sigma and C. Tau sigma here with I specify tau sigma because if you are in a conductive form, this tau value is the inverse of the frequency where the imaginary conductivity has the maximum. If you write the classic Pelton model in the resistivity form, it would be tau rho. It would be the inverse of the frequency where the imaginary resistivity has the maximum. Okay, and this is the classical spectrum, sigma 0, sigma infinite, that depends on sigma 0 and M0. And then again, this was tau sigma. So the inverse of tau sigma is the frequency. And C controls the width. So smaller the C value, bigger the width. And again, now I'm showing you not the maximum Paysenko model, but the maximum imaginary conductivity model. So what we look at is the maximum imaginary conductivity in the imaginary part of the spectrum. And then we use as second parameter instead of M0, sigma second max. This is different from the MPA, and the difference is that you can put here the maximum imaginary conductivity, you can put here the maximum phase shift, you can put here the minimum imaginary resistivity. Any of them works well. Where the idea is to look for maximum instead of looking for M0. And then, so this is homogeneous space, time domain, galvanic data, and these are the distribution of the 4 parameters. So sigma 0, M0, tau sigma, and C. And these are the spectral distribution, the distribution, right? So for M0, we have more than half a decade of equivalences, and this comes from the equivalences in C, because they are correlated.
Oh, sorry, I missed. Try this again.
So this is from an CMC inversion. So this is a Markov chain Monte Carlo inversion with 10 millions of repetition of an homogeneous space.
Okay.
And what we're looking at is that the distribution of the 4 parameters. I'm not showing you the correlation, but only the final distribution.
Yeah.
So this is sigma 0, M0, tau sigma, and C. And the problem is that these two are strongly correlated, so you can get a bigger M0 value, you get a smaller C value, and it's the same. That means that when you do an linearized inversion, your C section is a mirror of the M0 section. So you're not really doing a good job. And this is the maximum imaginary conductivity model, where here we have sigma second instead of M0. And in this case, the standard deviation of the distribution is less than 1/3 of the standard deviation of M0. And that's for free. So you have the same data, you have the same model parameters, but this parameter is by far better resolved. My claim is that the imaginary conductivity is by far more exciting if you want to play in a quantitative way with IP inversion, because this sigma second is the imaginary part of the extended Archie's law that you always find of any kind of IP petrophysical equation. So it goes directly where the petrophysical equations are expressed. This is a profile measured in Samsung, I think. So this is a classic call inversion. So we have sigma 0, M0, tau sigma, and C on the right. So sigma, M0, tau, and C. On the left, we have the standard deviation factor. So this is the linearized analysis. Where this analysis is G transpose C D to minus 1 G plus CR. I mean, there is also the regularization here, otherwise it's singular. And again, where it face down is where it's only constraint driven. So you see, and here in black, we have the dy. There's a dy computation that takes into account the parameter correlation. The message is that here the depth of investigation for M0 is less than 1/2 the one of resistivity. And it's similar to the depth of investigation of C, and tau is by far shallower. So this is the classic inversion, and this is the maximum imaginary conductivity inversion. And sigma second max in this case goes more than twice the depth, and it has also geological meaning because it fits the T layer there.
So can you explain again? So how do you get your depth of investigation then for each of the parameters?
So the depth of investigation is okay. It's not super easy, but the idea is to do something like that. So let's say that we have 3 model columns in our 2D inversion. Then for any depth, I accumulate the Jacobian. So I consider these cells as being the same cell. And then I compute the analysis of this cell, the data-driven analysis, where you do G transpose CD minus 1 G, where the data are all the 2D data. So this will give us a standard deviation factor on this cell as a unique cell. Right? Yeah. But in this cell, for each of these cells, we have all the parameters. So in this G, you have the Jacobian for all the parameters. This means that here you are taking into account the correlation between the parameters. So if the parameters M0, rho M0, tau, and C are correlated, then when you invert this matrix, you will get a smaller, a bigger standard deviation. If they are completely uncorrelated, then it will be the inverse of the diagonal. right? So the problem is that here, in this matrix, we have not only the diagonal, that means all the parameters are independent, but a lot of elements also outside. That means that this standard deviation factor on this model would be bigger if you have correlation. Yeah, you can do the same with one parameterization or the other, and then you can fix a threshold. So I want anything below this depth within a factor of 5, or within a factor of 2. And you get the DOI.
Okay.
So that's my way of computing DOI with correlated parameters. It's not it's my way. But this is why I'm also showing here the analysis, because this is Tarantula and Ballet way, so this is more established. So this is the classic sensitivity analysis with regularization. And if you look this and this.
So this is a posterior analysis, right?
Yes, this is a posterior analysis, because this is 2D linear inversion, ground-based.
Yeah.
Okay. And again, these are the two inversions, one close to the other. So why go for the new implementation? Because you go more than twice as deep. And I think it's easy to sell like that. With the same data and the same list. Sadly, for everybody, it's not as good as for galvanic ground-based. It's better, but not that bad.
Quite convincing.
Okay, and now if you want, I think, oh yes, simply to say, so you go deeper, you have smaller correlation, better resolution. And again, there is a closer link to Archie's law. And this is what we can see next, if you are willing to see how to compute the Arch permeability from like
More than willing.
Yes. Okay, so now what I'm trying to convince you is that we can get good estimate of dry permeability from ground-based galvanic DCIP data without any calibration. Let's see if I succeed. So we start with the definition of permeability, and this is simply Darcy's law. So you have a different pressure, you have a section with the water flowing here for length L, and then the discharge through the system is equal to the permeability. That is what we look at, multiplied by the different pressure, the section, divided by the distance, and the viscosity. This is just to introduce K. So what we're going to try to do now is to estimate K. And we are going to show it in square meter units. And the basis of all our work is the fantastic work from Andreas Weller, Slater, Andrew Billey, and company, that they took or at least many of the published data in the last 20, 30 years, and they tried to put all of them in a kind of same plot and try to link K measured with K estimated from IT in terms of sigma 0 and sigma second. Where sigma 0 is the DC conductivity without significant P. So actually this should not be sigma 0, this should be sigma bulk. So it's sigma 0 without the surface conductivity. And sigma second is the imaginary conductivity at 1 Hertz. Why at 1 Hertz? Because it's fast to measure and robust. And then if simple things work, we are finished. So it's completely phenomenological. But this equation works on 6 decades on many unconsolidated samples from different experiments. All of this is saturated and consolidated. So the idea is that, okay, but we can invert for these two parameters. In the MIC model, we have sigma 0 and we have sigma second max. In theory, we can also compute sigma second 1 Hertz. But the difference between the maximum sigma second 1 Hertz is negligible. So our idea is that can we stick here sigma 0 and sigma second from the inversion and see what we get? So I'm going to show you first some LOC data, and Niels knows perfectly what it is, by simply measuring IP in a ball with electrodes. And the idea with the LOC method is that we don't use drilling mud. So this is in contact with the real formation, so it should be quite undisturbed. At least this is the hope. And then what we did is that we did 3 LOCs in Grinstedt in Denmark. So they were 30, 27, 10 meter deep, and we had 58 samples with grain size analysis for computing our permeability from grain size analysis, and we had also 9 slug tests. So what I'm going to show you now is the comparison between IP, the permeability from IP, and permeability from grain size analysis and slug test. So we look first at this LOC here. So this is the gamma radiation measured also with the LOC. This is the known lithology from Grinstedt. No, not from Grinstedt, but from the geologist. This is sigma 7 max from the inversion, where we have also the error bars from the posterior covariance matrix. Sigma bulk. And then we try again to use this equation, and we can compute K. So this would be our estimate for K with error bars. So this is, so you take the inversion parameter, you compute the equation, you propagate the errors, and you get K. And K is bigger, around 10 to minus 9, in the top part where you have the glacial sand, and then it becomes smaller where you have the bigger sand. So here it's less permeable. And these are thin clay lignite layers where we have the minimum. So this is.
It is also fairly small in the quartz sand.
Yes, that's what we get. This is the grain size analysis. And in my opinion, it compares quite well. And here there is no calibration. You take the exponent from the formula from the literature, and you use them. And when there is clay and it's really thin, okay, the measure from the lab is also smaller. That's understandable. And also the equation for the grain size analysis is also less valid. So again, where are the bigger approximations, we can discuss in that.
So can you just take that a little bit more slowly with respect to the grain size? Just how you're.
So for grain size analysis, this is not an easy trick in the sense that there are tens of different equations that link grain size analysis to K distribution. And then the idea is that, and when you look in the literature for each of these equations, the authors of the equation claim, okay, this equation can be used in this kind of soil. Then you take all the equations that are applicable on that lithotype, and then what we did was to do a dramatic average and to take the error bars as the error bar from the average. So here the error bars of this grain size analysis is the error bars that you get using different formula.
Oh, okay.
And I think our first approximation is not bad.
So in order to do that, you need to know what the
lithology
lithology is. And
yes.
then you've got to.
Yes, and this way, and we know the lithology, so we know what equation we can apply.
Okay.
But you have also the samples. Right? I mean, when you do this, the grain size analysis, you have the samples, so you know what samples you're looking at. On top, in magenta, we do have the slug test. So the slug test, they are even better, I would say, measure of K. They are averaged vertically, probably bigger. So here, in this slug test, the vertical bar is the 8 of the screen of the slug test. So give us somehow information on what we're averaging at. And the comparison is even better. So our estimate of permeability from IP looks quite reasonable. So this is the second LOC. Again, you go really in the right place. Here, probably we should not link them. I mean, we miss the data in between, so that's fair. They didn't probably took the sample because there was clay. And this is the third LOC here. So my claim is that we pick the trend really well, but we pick also the order of magnitude. And from an IP perspective, your aim is to get the estimate of K within one order of magnitude. Better than that is not possible in the lab. So one order of magnitude would be a great success. So these are the data on unconsolidated samples from the literature in the lab in gray. These are our slug tests. And my claim is that they fit completely within the lab results. Grain size analyses are not as good, but again, there are a lot of uncertainty also in the grain size analysis estimation. So I think that is quite a good result. This point here is where it's a thin fat clay where it's okay, I think we don't resolve it. So this is the second I look, and this is the third. So overall, we do almost as good as the lab guys. And we don't do any calibration. This is in the bottle. Let's go to the field. So now we have 14 profiles, 5 meter spacing in this long one, and 2 meter spacing in the short one. Gradient array to the inversion, and then this is K from IP versus K measured on 89 slug tests. And again, my claim is that we're doing a good job. And now I'm going to show you where the good ones comes from and where the bad one comes from. So we look at this profile now. We have the water conductivity derived from sigma 0. Here is a bit more complex, but let's make it easy. So we have the water conductivity where we take the sea conductivity and we calibrate it with the information factor. And this is our estimate of the hydraulic permeability from 10 to minus 14 and 10 to minus 8. And in terms of K in square meter, this is the right range. So again, these are 2D inversion. You take your data, you do the inversion, and you do the model. And again, this is the DOI.
And that's from the IP part of the 2D inversion.
Yes. So here the DOI honestly is not completely perfect because this is the shallower DOI of the IP parameters. Actually, we should use we should propagate the DOI as well. But it's close. It's a good estimate. So here we have the measure of the water conductivity in bottles. And maybe these are small, but you will believe me if I claim that these red values are perfectly on top of our anomaly, and the same here. So we have a quite good match with the conductivity. And the problem is that there was no knowledge of this conductive body. And we were claiming this was pollution. And I guess guys from video were not convinced at the beginning. Now they are. So what we did is that we said, you know what? We should drill here. So they went there, they drilled once, twice, 3 times, and they found our value.
So can you go back to the drill log? So we're looking at white and so here the idea is that where is white, there is no information. Where there is the color is where there is the screen where the water sample has been taken. Oh, okay.
So here, this screen has to be compared to the inversion, the same here, the same here, the same here. And my claim is that we're doing quite a good job. And this is for sigma water. So we found the pollution. And the story is, I think that the students that went there for the drilling they were almost fainting for the smell of the water coming out of the bowl. So it was polluted. Even if there is no direct link between water conductivity and pollution. So these are separate. But then again, here we have the direct permeability as well, from the inversion and from the slug test. And again, the blue values where there is the clay, they match really well. And the value below clay, they are sometimes slightly over or underestimated. So these were in the scattered plot, the points are far from 1 decade. And the reason is that, okay, below a chargeable body, I mean, knowing exactly if the limit is here or here is not necessarily easy. So at the boundaries, you might have some mismatch. And again, you have, of course, appearances in the sample inversion. But then you put your estimate of the clay from IP on the conductivity, and you say that so it's not that it's conductive because there is clay. It's conductive because there is contamination. Because when you have resistivity only, there is always the doubt. I mean, am I seeing low resistivity because there is clay or because there is contamination? Because there is contamination. And this is a way of proving it through IP. And again, you can get the model of the clay with a low permeable layer and of the plume. Put it together with the profiles.
Nice.
Conclusion, you can measure, you can map permeability to earty. I think we can say that. Almost as good as in the lab, where the almost as good means within the resolution that you have. But limitations are only in unconsolidated samples. You have the formula also for consolidated samples. The problem is that they depend really strongly on the formation factors, on the sigma value. So they are less stable, because when something depends really strongly on the formation factor, a knowledge of the formation factor from this only might not be enough. Only in saturated media, because this spectrophysical equation works when it's saturated. Even if you can try to extend them also in unsaturated using some capillary pressure equation for claiming how the water content goes with that. With that one, you can also correct sigma second and sigma zero and apply them also in the unsaturated. And of course, you don't want any other source of IP. You don't want a source of contamination. You don't want whole bodies, all the things that breaks down the assumption, the specificity. And that's it.
That's really nice. That's very nice. So what are the what are your sort of next steps through this as far as?
So next steps through that is we need more validation. So we need to have more data. I also an example of data acquired in Wieden in Zurich, measured with the Joseph Deutsch that we met 1 or 2 weeks ago, and they are almost as good as this in terms of match. So we get the K values correct. The problem is that what use to do of this K value? Because what we want is that the hydrogeologists use them, and the way in which we retrieve them is not enough. My point is that we get the value of the deterministic inversion, and we might easily, for instance, not see a thin sand layer between two clay layers, or a thin clay layer that can be important from an hydrological model, but it has not enough signature in our data. So the problem is that we need probably to go a step further and try to incorporate these estimates of the permeability in a kind of geostatistical model to try to either make cluster or even more interesting. So one thing I think is exciting, I don't know how much it's going to work, but it's exciting, is that if you define a field for K and you define a field for the porosity, that means somehow resistivity, right? And you can do it in a kind of hydrogeological framework without thinking about geophysical data. So you define your 3D distribution of permeability and porosity. But then I can compute an IP forward with that through the petrophysical equation. So I can tell to the hydrogeologist if that model will fit my IP data. And if you do it that way, you take out the regularization. So instead of trying to get one model that will have always problem resolution and regularization, what you can try to do is to compute the physical misfit of the hydrogeological model. And I think that one will be interesting. So this is where we are now.
So who else is working actively on this problem, going from IP to permeability?
In the lab, there are several groups. So there is Andreas Feller, there is Liz Slater, there is Andrew Billy, there are a lot of Germans, Andreas Earth, Borner, Bacher. So there are several studies about that. Honestly, my feeling is that the quality of the IP data acquired in the field so far has not been good enough. If you want to do this, you need good data and good inversion. And that's mandatory, in my opinion. Good data and good inversion is not necessarily easy. There are, in my view, it's two problems. First problem is that the German scientific community, that is by far the strongest in IP, favors frequency domain field acquisition for galvanic data. And frequency domain field acquisition, my claim is that it's easily 10 times slower and the data quality is also worse. So my point is that getting good data in a reasonable amount of time is a challenge. So this limits somehow the field. Second problem is that in any case, acquiring good data, good inversion is not as easy as doing normal DC. And then if your data are not good enough and you don't pay enough attention in inversion, then your match with the prior knowledge won't work. But in my opinion, the problem is in the inversion. It's not in the method. At least this is what I hope. If you want, I have another teaser. So,
It's also lunch.
but there is going to be a really quick teaser. So what we are seeing so far, what you were doing that was to remove the EM coupling, and then looking gate by gate and doing an inversion of each of them, right? Am I right?
Yeah.
The question is, but without any IP induction, is the approximation of separating the signal in independent gates good enough? Where my claim is it possible to obtain from purely galvanic 2D or 3D forward responses exotic IP decays, where exotic I mean completely negative or with change of sign? My claim is that not only it's possible, but in the real world, it happens quite often. So it happens often that when you measure data, as well as you do when you measure airborne data, you get the data, and the shallow part are all negative. What should we do? We take the absolute value. Are they wrong? We reject them. You do exactly as you've been doing in the EM community. First of all, you reject them. Or you try to take the absolute value, think that there is an error somewhere. The data are correct, and there is no error there. And the data can be fitted only with galvanic responses. And they come from, because if you start to put variability in your C and tau through the system, then in terms of superposition, you can get almost everything. And if you want, not here but there, we can go through some data acquired in Greenstead again. So this is why these data for us have been really painful, because inverting this data was not so easy. This one in particular, across the river, were easier, but the one in the length, they really look crazy. And the reason is that so this is one profile, 600-meter long, 5-meter spacing, acquired on the landfill. And what we're looking at is that in the pseudo section, we divided the section in a vertical column every 5 meters, and we look at the decays. So this is on the left we have the resistivity with the pseudo depth, and on the right we have the decays, color coded. And the color one are the data, and the black one are the fit. And if we go along the profile, we start to see things like that. These data here, with the circle on top, they are negative data. So this is a log plot with absolute values. But these data here, they are completely negative. They're somewhere in the same place in the section of the other. They are completely negative, and you can fit them with a poor galvanic model. These are completely negative. And now what I'm going to do is I go through the model, and I try to convince you that inverting this data has been painful. Again, we have positive and negative data in the same place in the pseudo section. Negative and positive. Negative, positive, positive, positive. Negative, negative, and positive, positive, positive. Negative, positive, negative, negative, positive, positive. And I think that we will get also some really exotic shapes soon. So again, my point is that you can get this kind of data, and these are real data.
So again, so you're
this is a gradient array, A, B, MN.
Okay.
No EM, only galvanic, real data, and fit with the Colco-like model.
And how do you know there's no EM in there?
you don't know for true, but what we see is that often at earlier times, so all the times that we're missing here is where we have often change of slope, and this is our cutoff for the induction. But my point is that if you model it without induction, you can still model the data. So this is not a proof that there is no induction, but this is a proof that without induction, that would be physically possible. And this is something you cannot get at all, I think, if you do the gate-by-gate inversion. Because you will need to get negative forward in a DC forward. It's not really super easy, right? Mm-hmm. Because these are also big numbers. As long as close to 0, I think it's possible. When they're big, I'm not sure.
No, I don't see why that would be a problem. You could quite potentially get negative numbers.
In a gradient-like? In a gradient-like, right? It's all on the surface.
Yeah, maybe. I have to think about that.
Okay, and this is my final message, just to say that things are complex.
So, Gianluca,
thinking about the overall sensitivity
are you assuming that
and then
these
the
data
sensitivity
are
function
IP effects
is
at all?
negative.
No, these are with plenty of IP effect at all. With plenty of IP. So all the decays are IP.
Depending upon
Sorry?
There's plenty of
where
negative
your
data.
And these came from IP.
potential electrodes.
Okay.
It seems like
What you're saying is they could also be inverted without any IP model, just the conventional model.
No. You can invert them necessarily with IP model, otherwise you have no decay, without any EM effect. So a purely galvanic IP model can get negative data, exotic shape, change of sign, sinusoidal decays. You can get whatever you want.
But you EM effect out, according to
It simply is not there. I mean, in our forward response, the effect is not. Yes. No.
So we didn't take anything out. We just the early data out. The earliest gates.
But that's what I mean.
Yeah. So,
and
there's no modeling yet.
No. So you just took them out because they were under suspicion of being
little snake on the early times. They have little thing.
Yeah, but the power is that is anything but easy. So my point is that maybe I don't find them here, but often you have data that go to small values at the early times for 2D effects, not for EM effects. And then it's a big challenge, right? Because an exotic shape is not enough for saying that one is EM. Can still be 2D effect.
So in your analysis here, are you still using a 1D to
2D?
This is 2D, all 2D.
You can get a negative also in 1D, but this is poor 2D.
So are some of these complications that you see there, are they due to 3D effects? Because, I mean, you are inverting 2D.
I think there are 1D effects when you have a resistive chargeable layer on top. Many of them are 1D. Sadly.
But 1D effects should not be a problem in 2D inversion.
No. Sadly, because when you have all these change of sign, if you have change of sign, different signs on, it's less rough. Let's say it's not always click and get one inversion. Sometimes we have to play more. And again, the processing is more difficult. Because when you start to have a lot of exotic decays, deleting another data, the shape is not enough. It's not any more point. And then you never know. Should I delete that or not? It's different.
So are these data, are they from up here or are we talking?
They are from down here. So same side, but a bit south, where it's more resistant. Because here is almost at ground level, but it's a bit more on the south, where it's resistive and dry and chargeable. We have this data.
Well, this is pretty tempting to sort of ask, like, okay, could we get this data set to see what could be done?
Sure.
And then
I think Segoy asked me the data. Probably I didn't get that. Of course, you can get the data. You're more than welcome.
Because that'd be interesting. I mean, you raised some interesting questions here, right?
I'm happy about that.
Yeah.
Sadly, more questions than answers. But that's
No, no, that's actually good. Right? I mean,
Well, that's where you have all the fun.
yeah.
Yes.
I mean, what's the joy in like, okay, here's some data, applied this algorithm that worked, but okay, great. Oh, I think there's quite a few things that you've opened up here that would be interesting to pursue. And definitely could do that.
Yeah.
You've made my day. There we go. Now we can go for lunch.
We're not going anywhere.
Oh, we're not going anywhere. Well, we're having lunch.
We're having lunch.
Okay, let's see.
The menu is quite similar to yesterday.
In that case, is there any chance I could have a chicken